Hi everybody, I am Giovanni Pagano, PhD in my first year at the University of Salerno, and today in this talk I will speak about the advantages of non-standard finite difference numerical schemes for differential problems. This is an ongoing work with my research group in Salerno with Professors Conte and Paternoster. Therefore, I am to start. Okay. Which is the aim? Which are the motivations of my talk? We want to explain the advantages of non-standard schemes that are explicit like standard schemes, but they are able to follow the behavior of the exact solution of the model of the problem we are interested in, like real models of ordinary and partial differential equation. Therefore, we consider real models of ODEs and PDEs that represent some real phenomena, such as epidemic situations or physical situations, chemical reactions, and so on. And yes, from these real phenomena, we can obtain models of ordinary and partial differential equation, and we know that the exact solution of these models must be, for example, positive, must be an oscillating solution, and so on. And we want that these properties will be preserved by our non-standard scheme with the numerical solution provided by our non-standard scheme. And non-standard schemes are still explicit, but they are explicit, but they are more stable, as we will see, and they follow these properties. So they are very, very powerful. Therefore, we will show these things in our talk. We will show firstly existing non-standard schemes, and on these non-standard schemes, we have done some numerical tests in order to show you the advantages of non-standard schemes, and therefore we will show you our construction, our non-standard scheme we have obtained on a real model for biological situations. Non-standard schemes, as I said, were born in order to solve ordinary differential equations and are explicit. Therefore, the scheme, the equation number 2, represents an explicit, a very general explicit numerical scheme that obviously will depend on h, therefore we consider constant step sizes, therefore will depend on h, that is the discretization times step size of the ordinary differential equation we want to solve numerical. So this is the shape of our non-standard scheme, of an explicit scheme in general, the equation number 2. And these are the two fundamental rules on which non-standard schemes are based on. Therefore, we can modify the classical first-order derivative, but we can modify also derivatives of order greater than 1 by making this type of substitution. So we can replace the classic denominator h, the step sizes, the step size of our discretization by this function phi of h that, for a matter of consistency, in limit of small step sizes must tend to h. And we can also approximate the terms of our model by non-local representation. And also in this case, in limit of small step sizes, these non-local representations must tend to the linear or nonlinear terms we are approximating. Therefore, we expect that non-standard scheme is not as accurate as the standard scheme, but we expect that qualitatively it is better because this function phi and these non-local representations must be chosen in such a way as to preserve the properties and also to improve the stability of the relative standard scheme. In fact, these are some functions that are in general used for no standard scheme, and this is a small proof of the fact that the Euler method, the explicit Euler method, with the substitution of h with this function, by this function phi of h in this slide, Euler method became astable. This is an exact representation, and this is a no standard scheme. Therefore, by modifying the standard scheme for Euler method on the test equation, we are analyzing the stability of Euler method, so we are considering the test equation. By modifying h, by substituting h with phi of h, we obtain a numerical scheme that is stable and is also exact on test equation. Therefore, what we want to do, our aim is in gaining numerical stability. So we want to choose some properties of the model we are approximating, and we want that our numerical solution provided by the non-standard scheme we will use. Yes, we want that our non-standard scheme, our non-standard solution will be able to grasp, to follow these properties, the properties of the exact solution of the model we are approximating. We are interested also in accurate solution, but the main aim is in following the qualitative behavior of the solution and the properties of the exact solution of the model. This is, for example, the seed model. The models, the next two models of ordinary differential equation are treated by Meekens in this work here. In this case, we can compare standard and non-standard scheme. The non-standard scheme provided by Meekens. We know that seed model represents an epidemic situation. Therefore, the solution must be positive because each component of the solution represents quantities of people evolving in time. Therefore, the solution must be positive. But we also want that the solution will not does not explode as the time goes to infinity. And with these step size, that is an 8-step size, but the seed model represents the situation for high times. Yes, we want to control and to make provisions on our epidemic situation for long times. Therefore, we have to use high step size if we want a cheap numerical method. Okay. Therefore, with big step size, our non-standard scheme provides a good solution that qualitatively follow well the exact solution of seed model. The standard scheme provides numerical solution that is exploiting and also is becoming negative. In fact, Meekens use this non-standard scheme to preserve the positivity of the solution. These non-local representations are used to preserve the positivity of the solution, and this function phi in order to have a stable model, a stable numerical scheme. And this is the table in which we can also compare the errors in a smaller interval than the previous one. And in a small intervals, our no-standard scheme is also good. The no-standard scheme of Meekens, yes, we have only done in this case numerical tests. The no-standard scheme is as accurate as the standard scheme in small intervals, and in big intervals it is also convenient than the standard one, because the standard one provides a numerical solution that goes to infinity or becomes negative, and our no-standard scheme provides good qualitative solutions. And we can also see that the accuracy order of the convergence order of no standard scheme is equal to 1, as we expected. This is another example of no standard schemes for ordinary differential equation, a photoconductivity model, in which again the solution must be positive and must and we can see that the standard scheme provides a solution, a numerical solution that is exploiting. Our no standard scheme provides a good solution in this case, also with small step sizes. In fact, in this case, it is interesting to solve this problem in very high intervals. Okay, and in very high intervals, we can use this standard scheme also using a very small step size h. Okay, so if we don't want to over reduce the step size and to have a computational cost or computational time very high, we have to use no standard scheme. That is less accurate than the standard scheme, but it provides a qualitative good solution also for bigger step size, for higher step size, for larger step sizes, and therefore it is more convenient. We can also apply this technique for partial differential equation. In the case of partial differential equation, we have to apply the splitting technique. Therefore, we have the initial partial differential equation. We obtain from it several sub-equations. And it is possible that for these sub-equations, we know the exact numerical scheme. As in this case, linear advection and linear reaction. It is the no standard scheme provided by Meekens in his article, the article we have shown previous. And as we can see from numerical tests we have done, the no standard scheme provides about an exact solution, because the error is close to 0 in sense of machine precision. Therefore, for partial differential equation, we can use this splitting technique, dividing the initial partial differential equation in several sub-equations and finding exact schemes if it's possible for these several sub-equations. Finally, this is the model we have considered from Sherratt. This is a model that describes the coexistence of grass and trees in arid environments with less quantity of water. Therefore, we have three partial differential equations. We have a nonlinear term for each of these equations. Therefore, this model represents the situation in which trees and grass coexist in arid environments for a long time. Yes, for a long time. This is the solution provided by OD15S after assembly discretization in space. And we are interested in the construction of no standard scheme for this model because we can see that the solution is positive and also oscillates in space. So we want to preserve these two features of the solution with our no standard scheme, the positivity and the oscillating frequency. In order to preserve the oscillating frequency, we can use the exponential fitting technique that allow us to obtain exact schemes on splitting space functions. Therefore, if we know that the solution oscillates with the unknown oscillation frequency, obviously in space we can approximate this second derivative in order to be exact. The second derivative, yes, is exact on this fitting space. Therefore, that is a fitting space constituted by functions, trigonometric functions. Therefore, we are able to preserve the oscillation of our solution. And by doing so, we can see that these step sizes, the classical step size we obtain by approximating a second derivative in space, will be replaced by this function phi of h. Okay, so the exponential fitting in order to preserve the oscillation of our model, and these non-local representations in order to preserve the positivity of our model. Therefore, this is the standard scheme we have initially considered, and with these modifications, we gain our final non-standard scheme that is again explicit like our standard scheme, and we want it will be positive. It will provide positive solutions. Therefore, sufficient conditions to gain positivity from our solutions are these. These quantities in red must be positive, and these conditions can be summarized in this restriction on step size in time. These are some numerical tests in which we can see that the standard scheme provides a non-stable solution, a non-acceptable solution, because it is exploding and also it is becoming negative. Our non-standard scheme provides with the same values of the step sizes in space and time a good solution, a very good solution in a qualitative sense. Therefore, we have shown that non-standard schemes are very good if we want to preserve, if we know some properties of the model we are approximating, because it is also explicit, yes, but it is able to capture some interesting properties of our models. These are our proposal for future research. Therefore, we are going to modify again our model in order to grasp other properties such as critical points. We want also to obtain a less restrictive condition on the step size in time and so on. So these are some references. As I said, our work is an ongoing work. We hope to publish yearly. And so thank you for your attention.